So let's continue our discussion of slender members that we call beams, thinking about distributed loads. Instead of the loading on our beams being point loads, very concentrated application, a lot of times we have distributed loads. This could be a pressure, say water pressure or air pressure, and the most common distribution for the loads is a constant one, and that would be a constant pressure, say because of fluid forces, or a triangular distribution like I've shown on this cantilever beam. So if we consider this example of a beam cantilevered from a wall at point B, and it has a loading on it that it is a continuous pressure and applied in a triangular distribution, 0 at the left end A, that's the free end, increases linearly as we go back to where the beam is attached to the wall, and the distribution being linear is a function of the distance away from the end, x over L, where L is the length of this beam, x is the coordinate distance down, and then the magnitude at this end, which is the maximum, this case W naught, when x over L is equal to 1. So for this beam, let's see if we can't figure out what the shear and moment diagrams look like, and we will do the equilibrium approach of cutting the beam and finding out what moment and shear force must exist at every point along the length in order to keep the thing in equilibrium. The first step, though, is to find the unknown reactions on a free body diagram. And so our free body diagram is just going to be the beam itself, and we need to replace the wall with the reaction, shear force, and moment that the wall is exerting on the beam to keep this thing in equilibrium. So if we remove the wall, draw that free body diagram. So we replace the wall with the reaction at point B, which is drawn in the positive coordinate direction, and we can tell from our intuition that that is going to be the direction that the load will be applied to counteract all of this pressure hanging on the beam. And then the unknown moment at point B, which is the reaction of our constraint here, oriented again in a positive direction, but our intuition tells us here that although we're drawing an unknown quantity in the positive direction, that the actual moment is going to need to be applied this way to stop the beam, which has a tendency to deform in this direction. So it's going to take a correcting moment pushing up that way. But because we might not know that ahead of time, our convention is just to draw the unknown quantities in the positive orientation. So let's go about figuring out what these two reactions are for this distributed load. So then we're going to compute these unknown boundary forces, and we're going to do that by making use of the resultant of our distributed load. And this makes intuitive sense if, say, you imagine that I need to support a stick. And the stick has a force on it. Then to support it, I have to put a moment to resist the tendency for the stick to pull down, and I have to have a force upward, the shear force, to support that. But if my eyes are closed, I can't tell the difference between this and this, because the resultant is the same, and the line of action for these two 5s in the middle is equal to that 10 I started out with. So for the purposes of getting the force at my fingers, I can just use the resultant of the loads applied to my beam. However, there's a A warning here, this doesn't work for computing the internal shear and moment inside of our beam. So let's go ahead and find the resultant of this distribution to get these boundary reactions. And if we had a constant distribution, it would be easy to see that the resultant of that would be located right at the center of area for the distribution, which would be right in the middle. For a triangular distribution, if we take the integral of the area as it grows, we find that the center of area is 2/3 of the way down the beam from this left side. So the equivalent resultant is going to act right about here. And it's going to have a magnitude equal to the area of the distribution, which, as you remember, for a triangle is 1/2 the base times the height. So the magnitude of this loading is 1/2 of L times W naught. And so now for computing our reactions here, we're going to forget that we actually have a distribution, use the resultant, and we'll see that RB is going to be equal and opposite to that magnitude. MB is going to be equal to the negative of this reaction times that distance, which is 1/3 of L. So let's do that. And actually, I did all of this work and the camera didn't record, so I'm just going to give you the summary, which is probably better. Now that you've got the warning that you are allowed to take the resultant of the overall distributed force for getting these two boundary conditions, let's do that. And what that looks like is a resultant of a uniform distribution is easy to imagine. It's the area under the rectangle located right in the center. But we remember that the center of area is 2/3 of the way down from the tip of a triangle. So the resultant of this applied distributed load is a triangular resultant here, and it has the magnitude equal to the area underneath the triangle. So that means that the magnitude of this resultant for the use of finding the forces at my finger supporting this beam as a stick is 1/2 the base, and the base is length L, times the height, which at the magnitude is W naught. So this is the magnitude of this resultant, and it's located from this end 2/3 down the beam, which means it's 1/3 L from that point. So not thinking about the distributed load, but replacing its effect with the resultant, we can see then that the shear at the wall has to be equal and opposite to that when I sum the forces in the y direction. So RB is equal to 1/2 W naught L. And this moment is counteracting this magnitude, which is 1/2 L W naught over 2, at a distance which is equal to L over 3, because it's 1/3 of the way from this end. So the moment being the force times the perpendicular distance. So the moment is 1/2 L W naught times the distance L over 3, that gives us a counteracting moment required of W naught L squared over 6. So I use this resultant for getting the effect at this point. Now we've got our free body diagram, the beam, the reaction forces, and the distributed load, all the environment's effect on our free body, so we're ready to do our shear and moment diagram. And we're going to do this not with the singularity function approach, but just the tried and true intuitive make a cut in the beam. We make cuts at every place, starting at one end, where either the loading or the constraints change in a significant way. So in a complex loaded beam, it may require a number of cuts. Here, it's a nice example because nothing changes from one side to another. Clearly the force of this distribution builds up, but the form is the same. So we just have to make one cut at some distance x. So if we make a cut at any distance x, then lop off the part of the beam to the right, and we've got a free body diagram represented by this picture, where now at the cut my fingers are grabbing and need to provide a restraining shear and moment in order to counteract the effect of our distributed load. Now my warning was you cannot just use this resultant in the next cut, because that would suggest that any cut to the left of that wouldn't have an effect, and our shear would be 0. So we need to remember that this doesn't apply once we're doing the internal forces and moments, but the principle still applies, because we still have a distributed load, and at this end point, the effect of that triangular distributed load on my putting the equilibrium constraints, like grabbing it with my fingers, can be computed the same way using the resultant of this. So knowing that any point x by our distribution equation, at a point L, the right end is just W naught x over L. And in a triangular distribution, its resultant is 2/3 of the way down the triangle with a magnitude equal to the area under the curve. So the area here is 1/2 the base, and the base is now x, times the height, which is W naught x over L. So the resultant magnitude is 1/2 W naught x squared over L by just taking the area of that triangle. And it is applied at a distance from our cut 1/3 the way down this section, which has a length of x. So x over 3 is this distance. From that approximation, we can immediately write the equations for summing the forces in the y direction as 0, which means the shear force drawn in the positive sense minus this negative force of 1/2 x squared over L. Rearrange it for V, we've got an equation for V. Do the same summing the moments, about 0. If our point is the end of the beam, then we've got the positive effect of 1/2 W naught x squared over L acting at a distance of x over 3. When I multiply the force times the perpendicular distance, it's x cubed W naught over 6. And then we add to that, I've drawn the unknown m in a positive orientation, so I add m, rearrange m is equal to the negative of that moment value. So now I have my equations for shear and moment. Let's draw those out so we can see what the shear and moment diagrams look like. So if we plot out the equations for shear and moment, we get expressions that look like this, where V in X is to the second power. And then we've got X to the third here in the moment diagram. And one thing that I want you to notice from this specific example that generalizes to all of our cases, and that is, as a check to the shape, the value on the shear diagram is going to be the value on the loading diagram. So you can see the value on the loading diagram gets more and more negative as we move to the right. And I know that this looks positive, but it's all down. So really, for intuitive sense and accuracy, rather than draw the load distribution like that, we should have come in and done this, because the values are negative. And so at any point along the line here, the value on the Q, or loading curve, sometimes called WQ, is the opposite of the slope of the shear. So here, the value gets more and more negative as we move to the right. So we expect the slope of the shear to get more and more positive as we move to the right. And then the slope of the moment curve is the value of the shear curve with the opposite. So here you can see that the values increase in the positive sense as we move to the right. That means the slope of the moment diagram increases like the opposite of the value on the shear curve. So the slope of this is the opposite of the values here, and the slope of this are the opposite of the values here. And we can show where that comes from very easily, but just as another check, we can get the values at the right end by plugging in the overall length of L and seeing what our equations yield. So if we put in L for x squared, that goes out with an L on the bottom. So W naught L over 2 is the value we know shear to be on the right end. So that checks out. And then the moment at the right end at the position x equals L, L cubed over L is L squared, so we should have W naught L squared over 6. Negative, that checks out with the value we know to be on the right from the equation. So the equations seem to be right. The form of the graph seems to be right. Now we know shear and moment at every station. And we will see later in, I guess, chapter 6, how we take these values in order to get these stresses in the beam. So let's take a look at how we know what the relationship is between the values and slopes of these respective curves. So if we consider the differential relationships between those quantities that relate the slopes of the moment to shear to loading diagrams, we can consider an arbitrary loading Q. For simplicity, we'll make it a continuous loading of any shape, and we look at a very small section of our beam and do just a force and equilibrium balance over that length. So if we cut out this little delta x length of the beam, on the left side, we'll call whatever moment and shear acting there M and V in our positive sense on a negative face. And then on the right side, the value is going to be a little different, V by some delta V, and the moment by some delta M, as we're changing shear and moment as we're going down the beam. And then we've got the distribution of Q across the top. Since we're talking about very small delta x's, we'll make our engineering approximation that the reaction on the top then is equal to Q times delta x, where Q is just the mean of the small distribution over that. So our assumption is that the reaction due to Q is going to be just the mean value over that distance. So taking this approximation on a differential unit, we write out the sum of the forces in the y direction just by adding these terms together. And simplify it, we get an expression that looks like this one. And then same with the moment terms, add those up, set them equal to 0 because of equilibrium, and we end up with something that looks like this. And then if we let delta x go to 0 to get a differential form, then what we end up with, if we let delta x go to 0, as delta x goes to 0, delta v also is going to go to 0, so this term will tend to 0. These terms are differential terms, so we end up with this approximation of dv dx is going to be equal to minus q. And this one, with this approximation, we get dm dx is equal to minus v. And now we see why the slope of the moment curve is equal to the opposite of the value at that same location of the shear. And the slope of the shear diagram is the same as the opposite of the value of the loading diagram at that same point. And now that we have these differential forms relating V to M to Q, we can solve our beam relationship for shear and moment diagrams by integrating and using appropriate boundary conditions, which are the reactions that we solve for using the resultants of our distribution. And that is a second approach to doing shear and moment diagrams. The third approach in the textbook uses singularity functions, and I do want you to look at that and see where they're coming from, but I will be satisfied right now if you get comfortable with the equilibrium approach of imagining you're cutting the beam at strategic places and asking yourself, what moment, what shear do I need to put at the cut to represent the effect of the surroundings, or another way to think about that, to satisfy equilibrium of the remaining part of my beam in a free body diagram, and those are the values of the shear and moment diagrams at every place you make a cut. So that's Slender members for shear and moment diagrams that have distributed loading. And if you've got distributed loadings over sections of the beams and the point forces that we looked at last time, you just add the cumulative effect linearly and you can solve for your shear moment diagrams. Fantastic.